If you've already seen the first two videos relating to testing the JM Transistor Processor, you'll know that we have the first two boards completed and tested. So that is the clock board, that's the front board, and the control matrix, which is the second board back. That's actually enough for us to make the processor actually do something. We can run it. It won't be able to calculate anything or output data, but it will be able to go through all the various functions for carrying out its control tasks. So in other words, we can fully exercise the control matrix and make sure everything is working regarding the core of the processor. So we've got the test code loaded into the ROM, and the current state of the processor is how it will appear after a reset. So where we are at the moment is at the first machine cycle of the first instruction in the code. So in other words, we're at memory address 0, phase 1, and this is the LDA instruction. So the very first thing any instruction will do is to set the address of the data that it wants. So that will be of the opcode and any argument that it wants, and it will transfer that into the instruction register on the second board back, and then from there on the machine cycle will process that data. So the very first thing that any instruction has to do is transfer the current value in the program counter into the address register for the ROM chip. So in other words, it's going to select the correct address based on the current program count. So the current program count is obviously 0 because we're at the beginning of the program. In order to do that, this instruction cycle has already selected the LDA instruction. That's selected by default following a reset. You can see the opcode is reset to all zeros, and if you remember the table that tells you what each opcode does, if you look at that, you'll see that opcode 0000 is indeed the LDA instruction. So in order to get the data from the memory chip, what we have to do is latch the current value of the program counter into the address latch. So to do that, we have the EP line set. So EP is enable program counter, and that puts the value of the program counter out onto the data bus, and you can see that here. The lower 4 bits are the address of the program counter, and that needs to be latched into the address register for the ROM. It's already at 0, but it's going to go through the process anyway because this could happen at any time during a program. It also has to latch the memory register, which is actually the address register. These two events don't happen on the same clock cycle. It is a two-phase clock on this processor. So the first phase will put the data out onto the data bus, and the second phase will latch that into the address register. So if we go through those two phases of the clock by pressing the single step button, I should say I've got it in single step mode here, then what will happen is we'll latch this data that was on the data bus into the basically the address register, which is just the lower 4 bits. The next phase of the machine cycle will transfer that data from whatever selected from the ROM chip into the instruction register, and you can see it's already done that. It's already transferred it. Because it's a two-phase clock cycle, there is some overlap in the essentially in what each instruction phase does. So every single clock phase will do something. If you want to see what each phase is doing, you can simply hold the single step button in, and you'll see which particular clock phase you're in. And there's obviously 2 phases per machine cycle phase. There's actually 10 steps in any given instruction. So we're now at phase 2. So phase 2, we need to transfer the data from the ROM chip into the instruction register, and so to do that we have the CE line, which enables the tri-state buffers for the ROM chip. So it enables the ROM to put its data out onto the data bus, which is already done. You can see this is the data that is selected in the ROM chip, and you can see it's now out on the data bus. And if we look at the program that we're trying to run, you'll see that the first instruction should be 4 zeros and then 4 ones, and that's exactly what we've got. So it's successfully put the first byte of data in the ROM out onto the data bus. We then need to latch that into the instruction register, so the LI LED is on as well. And again, these are done in 2 separate phases to avoid any possibility of a conflict or contention on the bus. So the machine makes sure that the data is out on the bus before it tries to latch it into any registers. So those 2 actions are done on separate phases of the clock. Also, in phase 2 of every machine cycle, the CP LED will come on. CP is count program, and that will cause the program counter to increment on the next clock phase. So although it hasn't incremented yet, the next time the clock goes high, this will increment. It's kind of a secondary task as far as the instructions are concerned, but we need to make sure that the program counter is incremented as early as possible in the machine cycle, because if the machine is going to perform a jump, then we need to make sure that we don't increment the program counter after the jump, because a jump is essentially reloading the program counter with a new value. And if we increment the program counter after that's been done, then obviously we'll be pointing at the wrong address. So we've used the program counter value to get the data from the ROM, so it will immediately after that increment the program counter. So we'll now step on to the next phase of the machine cycle. So you'll see that the program counter did increment. So the next byte that we're going to load from the ROM is the argument or the data that was at the address provided in the argument to the instructions. In this case, the argument was all ones, and that, if for this instruction, constitutes an address. So in other words, we want to load the data value that's at address 1111. And again, if we look at the program, you'll see that the data at that address is 010101, etc. And that is indeed what's showing on the data. That now has to be put out onto the data bus so that we can access it, load it into the accumulator. So we'll go to the next phase, and you'll see that on the data bus we do in fact have the data value that's being presented by the ROM chip, and that's done again by the C line being asserted to allow the ROM to put its data out onto the data bus. And then we have the latch accumulator LED on as well, and again these are done on separate phases of the clock. The data is put onto the bus in the first phase, and then it's latched into the accumulator on the second phase. The accumulator is not there, of course, it's on a separate board. You'll see that the ROM chip often puts data out more than once on a single instruction, and that's because there may be arguments or extra data required for the instruction. So it may be that it has to load 2 bytes of data from the ROM chip for a single instruction, and that's all taken care of by the control matrix. So we're now at phase 4 of the current instruction. There are actually no more actions required for the LDA instruction, so the next phase will just simply return everything and prepare the processor for the next instruction to be carried out. So you can see that although we're on phase 5, no LEDs are illuminated because there are no actions required in phase 5 of the LDA instruction. Some instructions require actions in all 5 phases, some in fewer, but it's a fixed length cycle on this machine. That's how some modern processors are optimized. They will perform fewer clock cycles for some instructions. Okay, so the next instruction in the program is to add a value to register A, or rather the instruction that we want is going to be 0, 0, 0, 1, 3 ones and a 0. So that's what should be loaded as the next instruction. You can see the program counter is now incremented and pointing at address 1. So the first part of any instruction is to fetch that information from the memory chip. So you can see here that the first step, as previously, is to enable the program counter so it puts its current value out onto the lower 4 bits of the data bus, and then the LM latch memory LED is illuminated, so we're going to latch this, and then we'll go through exactly the same steps as we did previously to get that information into the instruction register. So in other words, we're going to transfer these values into here. So if we go through and do that, you can see we have successfully transferred the argument directly into the instruction register. And if we go on to the next phase, you can see that the opcode has now been successfully loaded and we have the add instruction LED illuminated. And it will now go through and complete the steps required for the add instruction. Once the add instruction is complete, it will move on, it will load the next instruction from the ROM, etc, etc. It'll just keep going, loading instructions and processing them in exactly the same way. That's all a microprocessor does. We'll look at jumps and more complex programming in a later video once the entire machine is complete, but I just thought you'd like to see the basic machine up and running in its most simple form. So what I'll do now is I'll switch it into... Okay, so I've switched it to run continuously using the slow clock. I've also set one of the option dip switches so that we can see it continually performing the same or running the same program. Otherwise what would happen is it'd run to the first halt and then it would stop. With this dip switch set, then what will happen is when any halt instruction is encountered, it will cause the processor to reset, and that will take it back to the start of the program and it will just keep running the same program. So that's what it's doing now, it's just running through that program we just looked at. And then it's resetting when it reaches the halt and running back through the program again. So that's on a slow clock. If we set it to a fast clock, then this is really if you want to actually do something with the processor and connect the output register to something. All the LEDs appear to be on continually simply because it's cycling so fast that you can't see them switching individually. You might get some flickering on the camera, but that's more to do with the frame rate of the camera than what the LEDs are actually doing. Me looking at them now, none of them are flickering. And if you want to, you can connect an external clock and run it up to much higher speeds and potentially do something useful with it. Okay, that's it for this video. We'll come back and look at testing the next two boards, and then once they're complete we can look at testing and programming the entire processor and maybe making it do something a bit more useful.